Hi. The main challenge in calculating limits is handling indeterminate forms. These arise due completing terms in an expression, and it is therefore extremely important to determine which term, if any, dominates. But what causes one term to prevail over another, thus resolving their indeterminacy? This video introduces a key concept for making comparisons, the concept of order of magnitude, and in particular the notion of little o, a shortening for little order. Consider, for example, an indeterminate form of type plus infinity minus plus infinity, such as the limit for x going to certain x star of f of x minus g of x, where both f and g tend to plus infinity. If one of these two terms, say f of x, is much larger than the other, we can factorize as follows, writing the limit as limit of f of x times 1 minus the fraction g over f. Now, it is clear that if this fraction goes to 0 when x goes to x star, the parenthesis goes to 1, and we transformed the indeterminate form plus infinity minus plus infinity into plus infinity times 1, which is no longer indeterminate, allowing us to resolve the limit. This motivates the following definition. Given two functions f and g of variable x and the point x star that can be real or infinite, we say that g of x is little order, or shortly little o, of f of x at point x star if the limit when x goes to x star of the ratio g of x over f of x is 0. The idea is that if this limit is 0, the fraction is very small around point x star. So it means that the numerator is much smaller than the denominator. Notice that this definition applies when both f and g goes to 0 and when also they go to infinity. Let's illustrate this definition on some simple examples. In this first example, we have x and x squared, and we claim that x is a little o of x squared when x goes to plus infinity, as the intuition may suggest. In fact, if we take x and we divide by x squared, we get just 1 over x that clearly goes to 0 when x goes to plus infinity. So this, according to the definition, means exactly what is written there. We can extend this property comparing two powers, x to exponent alpha to x to exponent beta. Now we have that x to exponent alpha is a little order of this x to exponent beta, even if the exponent alpha is smaller than beta. And in fact, we can verify this because if we take x to alpha divided by x to beta, this can be written as 1 over x to beta minus alpha. And since under this condition this exponent is positive, this power goes to plus infinity, and therefore the fraction goes to 0 when x goes to plus infinity. Be careful because comparison can be made between two powers also in 0, where they are both small. And in this case, the conclusion is opposite. The power is smaller when the exponent is bigger. In fact, if we redo the calculation x to alpha over x to beta, we can write this as x to alpha minus beta. Now, since here x is going to 0, and when this exponent is positive, this will go to 0, and only in that case, so only when alpha is larger than beta. We can also compare two exponentials, for example, at infinity, and we have that a to x is a little order of b to x if b is larger than a. An important comparison is between exponentials and powers at infinity. In this case, we have that powers are always little order of exponentials, whatever is the exponent of the power, alpha, positive, and whatever is the base of the exponential, greater than 1. Similarly, logarithms are lower order, so are little o of powers, whatever is the base of the logarithm and whatever is the exponent of the power. But when we compare two logarithms, for example, we know that there is a conversion formula for a logarithm in one base to the logarithm in another base. So we may imagine that the duration is just constant and it cannot go to 0. Let's now see an example of limit calculation that uses this comparison. We want to compute this limit, the limit for x going to plus infinity of 4 to root of x plus sine of x to x divided by 2 to x plus x squared log of x. Now, since this is a complex problem, we split into this discussion of numerator and denominator, and then we put together the information we gather. So for the numerator, we have that it is equal to 4 to root of x, that clearly goes to plus infinity, plus sine of x to x. Even if x to x goes to plus infinity, sine does not have a limit. In any case, it is bounded, and therefore we may expect that this term will dominate. In fact, if we factorize that 4 to root of x, we get 4 to root of x times 1 plus 1 over 4 to root of x times sine of x to the x. Now, we can notice that this goes to 0 because, as we said, this exponential goes to plus infinity. And despite this has not a limit, this is bounded. And since it is bounded, we can say that it is infinitesimal times bounded, it is infinitesimal, and therefore this product goes to 0. The parenthesis goes to 1 now, and we conclude that the numerator is like 4 to root of x times a quantity that goes to 1. So in particular, it goes to plus infinity. About the denominator, there is no question about the limit because the two quantities are not in competition. They both push to plus infinity. But clearly, the exponential looks to be bigger than the other term. And in fact, if we factorize, we see that this becomes 2 to the x times 1 plus x squared log x divided by 2 to the x. Now here we have to be a little bit careful with the explanation why this fraction goes to 0. Because if we divide the fraction in this way, saying that x squared is little order of 2 to the x, at infinity, this part goes to 0, but this part goes to infinity, so we would get an indeterminate form. However, we can easily solve this issue. We add an x here, so dividing and multiplying by x, so this becomes x cubed. Now, again, x cubed divided by 2 to the x goes to 0 because the power is a little order of the exponential. And on the other side, we have another fraction, log x over x, that goes to 0 as well because log of x is little order of x. Therefore, we can say that the denominator is 2 to the x times something that goes to 1. If we now combine the two informations, so we have that n over d is equal to, so numerator is 4 to root of x times something that goes to 1, divided by 2 to the x times something that goes to 1. We can write this as a power of exponential with base 2, so 2 to exponent 2 root of x. And therefore, this becomes a unique exponential 2 to exponent 2 root of x minus x times the ratio between two factors that they go to 1 is a fraction that goes to 1 by rules of calculus of limits. Now, this is a quantity that clearly goes to minus infinity because minus x dominates root of x, and therefore the exponential goes to 0, times this expression that goes to 1 yields a limit equal to 0. So we conclude that the proposed limit is equal to 0. Great. Now it's your turn. I recommend starting by practicing comparisons between quantities and applying the concept of little o to calculate limits like the ones shown here. You can also consider this problem, which is not a problem with comparison at infinity. It is in 0, but where one of the quantity is in the product. When one is going to 0, the other is going to infinity. But you can easily figure out. And moreover, this is a very useful limit in several situations. So good luck and have fun.